Okay, so I'm going to review the torque quiz, give you the answers quickly so that can hopefully help you prepare either for a retake or the upcoming test. So we want to find the center of mass of the cannon / ball. I'm going to use this as my 0 point, my reference point. So I'm going to say how far away is this from reference point. So that's going to be 0.5 meters times the mass of the cannonball, 20 kilograms. Okay, and by the way, the center mass equation is just simply equal to the individual masses times the distance, the sum of all those divided by the sum of the masses. Okay, now here's a part where many kids make a mistake. How far away is the cannon itself, the barrel, from that center mass? Well, the cannon barrel is located right there at its center of mass. In other words, I can reduce this whole barrel to that one point, independent of the ball. And so that value is, so the mass of the barrel is 100, and we are 1 meter away from that. Okay, and then I'm going to divide that by 100 plus 20. So I get 0.92 meters from the left. That's where I referenced it. Okay, then we fire the cannonball. And the barrel, implying this, is the barrel is not held down by anything. So the cannonball is going to go forward. The barrel's got to recoil. Well, that's action-reaction. That's a conservation of momentum. But to ask, what's the center of mass a certain amount of time? Well, the center of mass is still 0.92 meters. Why? Because there's no external force to the system. And if there's no external force to the system, then there can't be any change in position of the system. And that change of position of the system is the center of mass of the ball and barrel. The ball and the barrel will move away from the original points, but the center of mass will not. That's a very, very important concept that we want to continually reinforce. Okay, then it asks, how far will the cannon have recoiled after 5 seconds? So even though the center of mass doesn't change, the cannon will recoil. So to figure that out, I want to figure out the velocity of the cannon. So I'm going to say sigma p equals sigma p prime. Sigma, and that's all 0 because nothing was moving at the beginning. So what I can say then is the p of the cannon is equal to the p of the ball. And the p of the ball, based on the information given, is going to be 800 kilogram meters per second. So there is 1 point. Okay, figuring that out. This. Then I can figure out the velocity of the cannon by doing p over m of the cannon, and that is 8 meters per second. So there's your second point. And then where is the cannon? Well, I'm going to say its speed times the amount of time, which was given as 5 seconds. Okay, and that gives you 40 meters. You could try to do a center of mass equation and get that. So you would say the other alternative is just say 0, because you know the overall center of mass is going to stay 0. So that's x is going to equal the mass of the cannon times some other x, I'll call it x prime, plus 20, that's the ball, times 200. In other words, it'll have moved 200 from the time it was fired all over 120. Why do I have 150 there? I don't know, but it's 120. And so if you solve that, you also get 40. Moving on. So this problem gave us a lot of trouble. I did a very similar problem in the notes. And it's just identifying torques and why something either tips or slides or does neither. Okay, so the first thing we had to do is draw a force diagram. And actually, before I get to that, even though there's no actual hinge, it does pivot. You got to establish the pivot point. Okay, and the pivot point is going to be about that corner. Since we're trying to pull the mass in this general direction, even though we're not directly doing that, it's going to pivot about that corner. So that's very important for establishing our lever arms and therefore our torques. But before we do that, let's draw our forces. There are 4 forces. One is given. Okay, so I'll just call that a generic F. There is mg, which is acting right there. There is friction, which is acting right there. And then there's a normal force, which is acting at that same point. Okay, so right away I'm just going to say these do not exert a torque. They're not going to come to our torque equation because they pass through the pivot point. And so remember, if your line of action passes through the pivot point, there's no torque. So I'm just going to erase those for now. Okay, so I say, hey, there's a clockwise torque on that block. Label the center of, label the lever arm. Well, you got to understand is these are the two forces creating a torque. One is trying to pull it clockwise. It's actually this guy, right? So if I take this guy and break it into an Fx and an Fy, okay, we can understand that this is trying to rotate the block that way. That's counterclockwise. So what's preventing it from just going like that? Well, again, if here's our pivot point, you got to understand that gravity is exerting a torque, right? There's a line of action. So there's my lever arm, and that lever arm is trying to pull it back that way. In other words, if I tip this just a little bit, it will fall back as long as the angle isn't too big because of this torque. So anyway, that means our lever arm for the clockwise is 0.2 meters. It's this half of the width of the block. So when I want to calculate the torque, right, that tau clockwise is going to be the force of gravity, mg, times the 0.2. Put in the numbers, okay, and you get 39.2 meter newtons. I'm not going to worry about positive or negative because I'm just going to compare clockwise and counterclockwise. So the counterclockwise torque is due to this Fx. So the lever arm, so this is 3 points. This is 2 points. 3 points is identify that our counterclockwise is 0.8 meters. In other words, it's half of this distance because the force is acting up through the center of mass. Okay, now the counterclockwise torque is going to be a force. Well, which force? It's going to be Tx, and multiply by that counterclockwise lever arm. So you have to do a separate calculation. How do you calculate Tx? Well, you have two choices. You can say it's equal to T sine 15 or T cosine 65, or I should say 75. Okay, so I'm going to stick with the T sine 15, and then I've got to make sure I multiply that by 0.8. That's my lever arm, and then I get 12.4 meter newtons. And that kind of makes sense. This force right here is almost all vertical, so it's trying to lift it, but it's really not trying to tip it. So there's a very small amount of torque on that. Okay, now D was a little bit more involved. Find the net horizontal force. This is just review. Okay, so our net horizontal force, you should do it in two parts. There's 3 points for this. So first one, and I'll get to this, is you're going to look at, you're going to say it's F of x, and then there is a force of friction. Remember that force of friction vector we drew earlier. So F of x, we said earlier, is, I called it T of x before, maybe I should call it F of x. Hopefully that doesn't throw you off. Is nothing more than F sine 15. And if you calculate that, you should get, 60 cosine of 15. Let me double check my notes here for a second. Yeah, 60 sine 15 or 60 cosine 75 degrees. Either or, you should get a value of about 15 newtons. And then if you do a separate equation for friction, that's fuffing, okay, where the normal force is mg here, and you plug in the numbers, you should get about 88 newtons. And so so if you get these two values, you got 2 of the 3 points. The mistake that people are making is you're calling one positive and one negative, adding them and getting a value of, let's say, 62 or something like that. It doesn't work like that. This calculates the maximum amount of friction. There's no way friction can exceed this. Otherwise, it would just spontaneously going the opposite direction of what I'm pulling it. So what we have to recognize is this is less than the maximum value. So F net in the x direction is 0. All right, a very easy mistake to make, but we want, at this time of the year, at this level, we want to be recognizing that. Okay, now we get to the main point of the problem. What's going to happen because of that applied force? Well, in terms of tipping, the answer is no. Why? Because this clockwise force from the applied force is less than the counterclockwise force that we calculated there. Now, if you got the answers wrong and read in reverse, then you could have said yes and not lost points. In terms of sliding, the answer is also no, because the applied force here is less than the maximum amount of friction. And so it's not going to slide nor tip. Alrighty, so the last part is the multiple. Alright, so let's look at the multiple choice. I don't know why that's so large. So on this one, we did a lot with this type of problem in the homework. I just put it in this part, in this 3 points. So you have mg here, you have a T here, and you have some generic F that way. Okay, and I want to know what is the tension in the string. So you got to do this on torques. We said that again and again in this part because we don't know F, so we can't use balance forces. So I'm going to take this and break it into a Ty, and I'm going to break it into Tx. And what we want you to recognize is that there's going to be a clockwise, right, torque due to that. So in my work, I'm going to say ultimately it's not rotating because counterclockwise torque is equal to the counterclockwise torque. So the clockwise torque is due to T, and that's T sine theta. Okay, T sine theta. And that's multiplied by the lever arm, which is the full length of the rod. And that's going to be balanced by the counterclockwise torque of the weight. So that's going to be mg, and it's L over 2 because it's half the distance in. So if I go and solve, the L's cancel out. If I solve for T, I get answer D. Okay, so on this one, it's again balance of torques, and what I basically say is clockwise equals to counterclockwise, so one of the torques is equal to big M, L over 2, and that's going to be balanced by some distance x times 2M. So when I work it out, I get L over 4. A net torque causes rotation. Okay. On this one, all right, how far from the left end of the rod must be for the force to maintain equilibrium? Again, this is balance of torques. I have a weight, so this is 6 kilograms, so that means there's a 60 Newton force pulling down here. So I'd say 60 newtons times times half the length, which is 1 meter times 0.5, has to equal 40 times some distance x. Okay, and if we solve for that, you get 25 centimeters. What force is supplied to the rod by the pivot? In other words, what's this? Okay, well, if this is 40 up and that's 60 down, then this has to be 20 up. There's no horizontal component because there's no horizontal components to these. So that's why it's this. All right, I'm not going to worry about the bonus, but the answer is 5, 6, and 1, 6 coordinates wise. Okay, so if you still have questions from this, ask in class.